We will continue with the parallel RLC circuit or parallel resonance circuit. Okay, in many ways, a parallel resonance circuit is exactly the same as the series resonance circuit that we looked into the previous tutorial. The difference this time is that a parallel resonance circuit is influenced by the currents flowing through each parallel branch, okay, with the parallel RC tank circuit. A tank circuit is a parallel combination of L and C that is used in filter networks to either select or reject AC frequencies. Okay, a parallel circuit containing a resistor, inductance, and capacitance, which will produce a parallel resonance circuit when the resultant current throughout the parallel combination is in phase with the supply voltage. At resonance, there will be a large circulating current between the inductor and the capacitor. Due to the energy of the oscillation, then parallel circuit will produce the currents resonant. A parallel resonance circuit stores the circuit's energy in the magnetic field of the inductor and the electric field of the capacitor. This energy is constantly being transferred back and forth between the inductor and the capacitor, which results in zero current and energy will withdraw from the supply. At resonance, the parallel LC tank circuit light an open circuit with the current circuit being determined by the resistor only. So the total impedance of the resonance circuit become just the value of the resistance in the circuit, which is Z equal to R. This is the equation that we use to calculate the resonance frequency omega naught in radian per second. But if you want to calculate the resonance frequency in hertz, okay, we just use this equation. But the unit is in hertz. So in order to calculate the half power frequencies omega 1 and omega 2, okay, we use this equation given here. So notice that the difference between these two equations is only here. Okay, so this one positive, this one negative. Okay, next the bandwidth. Okay, bandwidth. The equation for the bandwidth is also same with the series RLC circuit, which is bandwidth equal to omega 2 minus with the omega 1. Okay, and the quality factor is omega naught over bandwidth, or equal to omega naught times RC, and also equal to R over omega naught times with the L. Okay, for the high Q circuits, which is the Q have a greater number, greater than 10, then the half frequencies are omega 1 equal to omega naught minus B over 2, and the omega 2 is equal to omega naught plus B over 2. Okay, we will look into the example 2 for the parallel resonance circuit. Okay, given a parallel resonance circuit here, so we have resistor equal to 8K, 8 kilo ohm, L is equal to 0.2 millihenry, C equal to 8 microfarad. So the first question, calculate omega naught, Q, and also B. Second question, find the value of omega 1 and omega 2. The third, you have to determine the power dissipated at omega naught, omega 1, and also omega 2. So the first one, we want to calculate the value of the resonance frequency, omega naught, the quality factor, and also the bandwidth. So omega naught is equal to 1 over CLC using the equation given in the previous slide. So we get 25k radian per second. So for the Q, R divided by omega naught times with the L. Since we already have the value of the omega naught here, so we use this equation. So we get Q equal to 1600. And for the bandwidth, okay, omega naught over Q. Since we already have the value of Q here, then we get the bandwidth 15.625 radian per second. The second question, okay, find the half power frequencies, which is omega 1 and omega 2. Since the value of Q is 1600, which is greater than 10, so we use this equation to calculate the half power frequencies omega 1 and omega 2. So omega 1 is equal to omega naught minus b over 2, so we get 24,992 radian per second. And then for the omega 2, okay, omega naught plus bandwidth over 2, so we get 25,008 radian per second. Okay, see, calculate the power dissipated at omega naught, omega 1 and omega 2. Okay, so at omega naught, so Z is equal to 8 kilo ohms, because we notice that at resonance condition, okay, it is purely resistive. So Z is equal to 8K. Okay, then we calculate the value of I naught, which is V over Z. Okay, we have the value of V, and the Z is 8 kilo ohms that we get here. So we get 1.25, okay, negative 90 degree milliampere. So once we get the value of I naught, we can calculate the average power dissipated at omega naught, okay, using this equation. So P is equal to 1 over 2, okay, I naught, we just take the magnitude, okay, times with the R. So we get the average power is 6.25 milliwatt. Okay, for the at the half power frequencies omega 1 and omega 2, okay, P equal to Vm square divided by 4R, which is 3.125 milliwatt. Okay, so for the exercise 2, you have to calculate the value of omega naught, omega 1, omega 2, and also Q and B. So given the circuit, given the parallel resonance circuit, which the value of R is 1000 kilo ohm, L is 20 millihenry, and C is 5 nanofarad. So you can check your answer and compare with the answer given in here. Okay, summary of the characteristic of a resonant RLC circuit. So this is the summary for the resonant RLC circuit. We have a series circuit. Okay, this one is the parameters for the parallel resonance circuit. So you can check the difference between these two parameters between series and parallel circuit. Okay, so that's all for this topic. I hope you enjoy it. Thank you.